I'd like to continue the discussion with the Thevenin theorems. We look at the simple example. I'd like to do another examples that we discussed when we look at the bridge circuit. If you look at the circuit, R1 times R4, that's 24. It's not equal to 3 times 12, so the bridges aren't balanced. So if you're interested in how much voltage you have across that resistor at point A and B, or how much current is going through it, then you really need to do 3 meshes or do 3 nodals. But you can do it with a Thevenin. So we want to replace the shaded area with a Thevenin equivalence model. So we're interested in what happened in the bridge to that resistance RFL, which is a load. So you identify this as A and B. That's your network. Everything outside the point A and B is equal to network A. So to calculate R Thevenin, you de-energize it. You put a short circuit here. And if you look at the circuit, when you short circuit the 72 volts, then the point C and C prime are exactly hooked up to the ground. So that means C is the same as C prime. So I need to bend this resistance R1 in a clockwise, counterclockwise direction. So to put those two in parallel, you do the same thing with R2. C and C prime is the same. So if I take this resistor and bend it over, put it over here, you haven't really changed anything in the circuit. So R Thevenin, then these two be connected in parallel, these two be connected in parallel, and the combination of those two is they're connected in series. So R Thevenin will be equal to R1 in parallel with R3 plus R2 in parallel with R4. 6 in parallel with 3 gives you 2, 4 in parallel with 12 will give you 3, so you have a total of 5 ohms for R Thevenin. And then for E Thevenin, you go back to the original circuit. This is open circuited here, and since this is open circuit, you got 72 volt directly across R1 and R3. You can do a voltage divider here, solve for the voltage V1. V1 will be equal to 72 times 6 divided by 6 plus 3. That gives you 48 volts. You do the same thing for the voltage V2. That's 72 times 12 divided by 12 plus 4. That gives you 54. So if you go on that loop, add up all the voltages, you pick a polarity here, so we assume this is plus or minus. If it comes out to be negative, then you change the polarity. So let's assume the E Thevenin is plus, minus like that. Go around the loop, minus to plus, it gives you plus E Thevenin. Then plus V1, minus to plus, plus V1, and then plus to minus is minus V2 has to be equal to 0. Solve for E Thevenin. Then it's V2 minus V1 is 54 minus 48. That gives you 6 volts. So that's your Thevenin model. Now, whatever the value of RFL is, you can calculate easily the voltage across it as well as the current through that load. Another example, let's say you have the following circuits. You want to replace the shaded area with a Thevenin. R2 is hooked up between this point to the ground. So if you redraw the circuit, that's hooked up to 10 volts to the ground. So right here, and this is hooked up to minus 6 volts to the ground. So if maybe plus minus to the ground is minus 6 volts. But if this is minus with respect to the ground, to make it plus, to just change the polarity to make it plus or minus. Easier to do. First, you want to calculate R Thevenin. So looking back this way, you're going to short circuit the 2 voltage sources. And you can see that R Thevenin will be equal to 1.4 kiloohms and plus these 3 connected in parallel. So it'll be 1.4 plus these 2 connected in parallel. You can do a total of the combination of 3. Or you can do 2 at a time. 4 in parallel with 6, that gives you 4 times 6 is 24 divided by 10 is 2.4. And then you combine that, the product divided by the sum, it gives you 0.6. So total R Thevenin then is equal to 2 kiloohms. Next, you look at E Thevenin. So you got 2 voltage sources. So open circuited here, looking back, we're going to call that E Thevenin prime. That's the contribution to the voltage E1 only, the supply E1. And then next, you short circuit E1 and look at its contribution for E2. I'm going to call that E Thevenin double prime. So for the E Thevenin prime, this is open circuit, so there's no voltage drop here. So if I look at voltage, measuring this voltage, would be the same as measuring the voltage here. V3, which is a parallel combination of R2 and R3. So if I look at the parallel combination of those two, which is actually 2.4 kilo ohms, then 6 volts is going to split up between R1 and 2.4 kilo ohms combination of those two in parallel. So that's a simple voltage divider. So E Thevenin then would be equal to E1, which is 6 volt, with that polarity, plus or minus. You've got to pay attention to the polarity, times 2.4 divided by R1 plus R prime total, which is 2.4K. That gives you 4.5 volts. For the contribution here, these are all connected in parallel. R1, I can put it on this side, make it R1 parallel with R3. You're not going to change the circuit. And then you do the same thing again. This is, now you have to pay attention to the polarity. This is plus or minus, then the E Thevenin double prime would be plus minus like that. So these two are connected in parallel, 0.8 and 6, that gives you 0.706 kilo ohms. Now 10 volts is going to split up between R2 and the combination of R1 and R3, which is 0.706. So it would be 10 times 0.706 divided by 0.06 plus 4K. That gives you 1.5 volts. Now because the polarity is different, so they're contradicting, it's opposing voltages, so the one with a higher magnitude, which is 4.5, it will determine the polarity of the total E Thevenin. So it would be plus minus like that, and 4.5 minus 1.5, it gives you 3 volts. So that's your Thevenin for that circuit. Now how do you measure E Thevenin and R Thevenin in a lab experimentally to do it? Well, if you look at this circuit that you want to replace it with a Thevenin equivalent, if you measure the voltage here, V open circuit, that's extremely simple. At a point of interest, the two terminals, you just put a voltmeter there with everything else is oscillated from it except network A is energized. And in this case, we give you 4.5 volt. But if you want to calculate it, just easier to just do source transformation here. 8 times 4 is 32. So you got plus or minus 32 volts here with 4 ohms connected in series with it. So if you go on that loop, minus 32 times the current of 4 times 1 plus 3, minus 12 volts. Actually going around with that direction, in the counterclockwise direction, it doesn't matter. It gives you 5.5 amps. For the total current, once you do the source transformation here, those two voltages add up, and then that's 44 divided by total resistance, which is 8 ohms. It gives you 5.5. So if I'm after this voltage from here to the ground, you can do it either way. You can calculate how much voltage you have here, which you already have is 32 volts. Then 32 minus the voltage drop across R2, it gives you V Thevenin. So 32 minus 4 plus 1, I'm sorry, before 1 because 4 will be connected in series with it. So 5 ohms you have connected in series, so whatever is dropped there is 5 times 5.5 amps. Minus 32 gives you 4.5 volts. Or whatever this voltage is, E Thevenin is equal to 3 times 5.5, but this one is subtracted from it, the minus 12 volts. Either way, it gives you 4.5 volts. For R Thevenin, this is open. These two are connected in series, so you got 5 in parallel with 3, it gives you 1.875. So that's the model. So if I build this model in a lab and put a voltmeter there, of course you're going to imagine exactly 4.5 volts. So it's really straightforward in a lab to measure V open circuit, which is E Thevenin. Just open circuit at terminal you're interested in, A and B, and just simply measure the voltage there. For R Thevenin, there's a couple of ways you can do it. Method number 1, you de-energize the network A, but you have to be careful in the lab not to put a short circuit across your power supply, because if you do that, you're going to damage the power supply. So the best thing is just to turn it off. One of the safest things is to do actually completely take it out of the circuit and just put a short wire that are 2 terminals that you had hooked up your power supply. And for any open current sources, just simply open it, leave it wide open. And then you just put an ohm meter across the terminals. And in this case, of course, you're going to get 5 in parallel with 3. It gives you, since there's no current flowing in here, just simply the resistance of 1.875. The second method is not to de-energize, leave everything in the way it is as a live circuit. If you look at the model, if there is no current flowing in here, if you measure the V open circuit, of course you're going to read 4.5 volts. So if you put some kind of a potentiometer in there and adjust it until you measure half of the E Thevenin, in this case would be 2.25, then R of L has to be equal to R Thevenin. So first you measure the V open circuited, whatever that voltage is, in this case is 4.5 volts. You hook up as a potentiometer to the terminal A and B, but only either the middle or either one A or B terminals. So you hook it up as a variable resistor, a rheostat, and you're adjusting it until the voltmeter across those two terminals of a potentiometer reaches half the open circuit voltage. So you make two measurements, V open circuited, and then put a potentiometer that adjusted until you get half of the V open circuited. And once you get that voltage, just take it out of the circuit and measure the resistance, whatever the potentiometer is reading between those two terminals that you had in the circuit. That gives you your R Thevenin. The last method, again, you make two measurements. V open circuit we already have with the previous measurement, but the difference is here is you measure I short circuited. So you make two measurements, V open circuit and I short circuit. If I look at the model, if I measure V open circuit, that's your E Thevenin. If I measure I short circuited, which is you can actually measure with an ammeter because ammeter has almost zero internal resistance, so you, in a sense, you're short circuiting it. The current that you'll be reading with the ammeter is just simply is equal to E Thevenin divided by R Thevenin. That's your I short circuited. If I solve for R Thevenin, then would be equal to E Thevenin divided by I short circuited. So V open circuited is your E Thevenin, so you make that measurement, and then you measure I short circuited here, and take a ratio of those two. Are probably the most straightforward. You don't have to de-energize the circuit at all. So most people prefer this technique. Now, with Norton's theorem, we talked about this before, that every voltage source with a serial internal resistance can be actually replaced with a current source equivalent. That current source equivalent can also be determined by what is called a Norton's theorem. It can be found to the source conversion as well. Norton's published his theorem about 40-some years or so after the Thevenin, but to me it's a direct source transformation, nothing really new. Mr. Norton said that any two-term linear DC network can be replaced by an equivalent circuit consisting of a current source and a parallel resistance, and you show in figure here. So at any 2 points in network A, you can replace it with a current source and a resistor which is connected in parallel with it. How do you do that? Other than the I Norton's, everything else is almost identical to what we did with a Thevenin, so we're not doing anything new. Step one, you remove the portion of the network across which the Norton equivalent circuit is found. So you identify the network A and B and open circuit it. And then you mark the terminal of the remaining two terminals network, which you call A and B, or some people call it X and Y. And step number 3, R Thevenin is exactly the same as Norton's resistance. So R of N is the same as R Thevenin. The process, how do you calculate and measure it, is exactly identical. So you de-energize it, replace all the voltage sources with a short circuit, and replace the current source with an open circuit. And then you measure the resistance at those two terminals. The only difference is in step number 4, to calculate I of N by first returning all the sources to original position before you open or short circuit it. And then you find the short circuit current. So the terminal A and B, you put a short circuit there, just simply put an ammeter to measure the current if you want to do it in a lab. But if you do it in a calculation, you just put a short circuit and then calculate the I short circuited. And then after that, you just, step number 5, you draw the Norton equivalent circuit, which is again, is exact source transformation. So if I have a Thevenin, to convert it to the Norton's, just take E Thevenin divided by I Thevenin. That was your I short circuit that we discussed already, and then you put R Thevenin in parallel, which is R sub N. Let's look at an example. It says find the Norton equivalent circuit for the network in a shaded area. So you identify it. So you open circuit point A and B, and that's your V open circuited. point A and B, and that's your network A. To calculate R sub n, which is the same as R Thevenin, just looking back and short circuited here, so you got 3 in parallel with 6, that's pretty straightforward, is equal to 2 ohms. To calculate I short circuited, you put a short circuit here, and you calculate that current. If I put a short circuit here, you automatically short circuit the resistance R2, so that's really out of the circuit. Then you got 9 volts across 3 ohms, 9 divided by 3, you got 3 amps is flowing through it. So that give you I short circuit, which is I of n, and just simply put those. But you got to keep track of which directions the current is flowing that direction. So that's your I sub n, and then put R of n, which is 2 ohms in parallel with it, and that's your R of n. So if you really want to calculate the Thevenin's equivalent for that circuit, you just do a source transformation here. 3 times 2 is equal to 6. And then put the 2 ohm resistor connected in series with it. So we're not doing anything new when we're doing Thevenin. Another example is this find Norton's equivalent circuit for the network external to 9 ohm resistor. Again, you identify it as point A and B. Looking back this way, you open circuit this. So you got 5 connected then in series with the 4 ohms. That give you 9 ohms for R Thevenin, which is the same as R Norton's. And then to calculate I short circuit, which is I Norton, you put a short circuit here, and you can redraw the circuit. You got 10 amps is coming out. It's going to split up between R2 and R1. So you do current divider rule. So I sub n then would just simply be equal to R of a 4 ohm resistor. So you multiply 10 amps, interested in this current, you multiply by 5, divide by 5, well, it's 4, it gives you 5.56 amps. You just put that in a Norton's theorem. And the other example, look at an example with 3 sources. Here it says substitute Norton's. Okay, for this example, it says find the Norton equivalent circuit for the portion to the left of A and B. So here, we're really not interested in anything in this part of the circuit. We're interested, we want to analyze this part of the circuit, so that's your network A. We want to replace everything to the left of terminal A and B, replace it with a Norton's. So I identify that. Okay, to calculate R Norton's, you can open circuit there and short circuit that, and that should be straightforward. You got R1 in parallel with R2. 4 times 6 divided by 4 plus 6, that gives you 2.4 ohms. Now to calculate I short circuit, you put a short circuit here, and if that's short circuit, of course, there's no current going to flow. You can take that out of the circuit. First, we're going to look at the contributions. So we got 2 sources in. First, we're going to contributions of E1. So we'll leave this one open. We're going to call that I prime n, and since this is short circuited, then the current I sub n prime just simply be equal to the voltage E1 divided by R1. That gives you 1.75. Next, we're going to look at the contributions of 8 amps. So we put a short circuit here, and then well, the polarity here, of course, would be in plus or minus. That's I sub n prime going from A to B. And for the contribution of 8 amps, it's going to go from, because the current is coming in, it's going to split up between these two. That one is shorted. This one is shorted as well. Okay, please pay attention to that. The current is coming in here. It's not going to split up because you have a short circuit here, which is the same as here. So if I take R1 and put it on this side, that one is also short circuited. So all that 8 amps is going to keep going on that loop. So I and double prime is equal to 8. But those two are opposing each other, so it'd be the total would be the difference between those two. 8 minus 1.75, it gives you 6.25 in upward direction from B to A. So put all that in. This is the part that we replace it with the 6.25 and R of n, which is 2.4, the rest of the circuit. Again, to determine the Norton's theorem experimental, we already did R Thevenin as exactly the same as R Norton's, but for just measure I sub n, we already did that with this method number 3 for calculating R Thevenin. So for the I short circuit, just put an ammeter at open circuit terminal at point A and B, and whatever that measure is I short circuited. All right, we'll stop here, and then we'll continue with the applications of Thevenin's, which is maximum power transfer, next time. Thank you.